Alright, so this video is on multiple bonds and something called sigma and pi bonds. So this is a continuation of our discussion on hybrid orbitals and hybridization, and we just learned the shortcut for predicting the hybridization of the central atom. If it has 2 electron domains, it's a sp hybridized. If it has 3, it's sp2 hybridized, and so on and so forth. So what we have yet to talk about, though, is something that contains double or triple bonds, and so that is the discussion for today. So before we truly get into talking about double and triple bonds, we're going to talk about something called sigma and pi bonds. So I have a couple notes written here, and the first thing that I've said is, so far we've discussed covalent bonds where the electron density, or the overlap, okay, is concentrated around what we're going to call the internuclear axis. And so what the internuclear axis is, I'll show you. So like, let's say we have an s orbital plus another s orbital, okay? And if I were to bring those two together to overlap them, this is the one that looks like the Venn diagram, so to speak. Okay, well, the internuclear axis is the line that connects the two nuclei. So if I have my first nucleus here and my second nucleus here, then the internuclear axis goes like this, right? My picture's kind of funky here. And so when you have overlap that occurs on the internuclear axis, that's called a sigma bond. And that's this overlap right here is occurring along the internuclear axis. You'll hear me sometimes refer to it as kind of an end-to-end overlap. Okay, because the overlap is occurring and they're like butting up against each other, so to speak. So that's called a sigma bond. Okay, it's still a covalent bond, but it's a sigma bond, and it gets this symbol sigma, which is a Greek letter, and so this is a sigma covalent bond. So we have other things that are sigma other than a 1s and a 1s. Let's say we had a 2p plus a 2p, right? So think about where the nucleus is, and maybe you've never thought about this. Let me change my color so you can see. In a p orbital, the nucleus is right here. Okay, so if I were to bring those two together, I get something that looks like this, and then overlap, okay? And again, don't lose track where your nuclei, there's one here, and there's one here. So where's the internuclear axis, the line that connects the two nuclei? Well, it goes like this. Okay, and again, we have overlap that's occurring along that axis, so this is also a sigma bond. Okay, and so far that's the only type of pictures we've been drawing. You probably don't know that, but if you go back and look at when we were talking about promotion and mixing of orbitals and hybridization, we were drawing sigma bonds, this end-to-end overlap. However, there's another type that can occur. And the second type that can occur is when bonding occurs perpendicular to the internuclear axis. It's called a pi bond. So the best example I can give you of that before we get into anything crazy would be a 2p and a 2p that are oriented along the y-axis. So if this is a 2py and this is a 2py, okay, and we bring them together, again, oops, that was supposed to be an equal sign. Keep in mind where your nuclei are. Okay, if I bring these two orbitals together, why isn't my pen working? I get something that looks like this, and then something that looks like this. Again, where are my nuclei? They are here and here. Where's the internuclear axis? Right here. And what you have to ask yourself is there any overlap occurring on the internuclear axis? And the answer is no. Look at it. The overlap's here above, and the overlap is here below. So you'll hear me, where I called sigma kind of end to end, I often refer to pi bonds, as kind of a, and this isn't like correct terminology here, but it's like a above and below bonding that's occurring. So I hope you can see the difference in those two, where sigma is an end-to-end bond, okay, along the internuclear axis, and a pi bond is where your overlap is occurring not along the internuclear axis. Okay, again, in my kind of silly terminology, it's occurring above and below the internuclear axis. Okay, so how does this affect us in our discussion? So I want to talk about an example problem. Okay, so let's say we have this. Okay, so this is a molecule. If I were to draw my Lewis structure, my carbons are in the center, my hydrogens are going to be out on the sides. I should have done a valence electron count. So I have 12 electrons, right? Carbon gets 4. Oops. 1, 1, 1, 1. So bond, bond. My picture is looking kind of funny here. Bond, 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 and then it's screaming at me to make a double bond with those 2 electrons. Okay, so let me redraw this because that was kind of messy. But this is what it would look like if I had drawn it a little bit nicer. Okay, and we could do a couple things based on what we've learned so far. We could talk about the geometry around each carbon. Well, remember this was a shape of a larger molecule. So around this carbon, it has 3 electron domains, 1, 2, 3. So that's trigonal planar. Same thing around this, trigonal planar. Again, now we can talk about hybridization. So we know it's got 1, 2, 3 electron domains. Each carbon does. And so 3 electron domains should give us a hybridization of sp2. Remember the trick. If it's 3 domains, then it has to be an s and however many p's add to make 3. So these carbons are sp2 hybridized. And would give us a geometry of trigonal planar around each one. And so my picture is pretty good. So if we're going to make an sp2 orbital, let's think about how we would do that. So let's start with carbon. So carbon has 2s and 2 p's. Okay, so I know I'm going to make an sp2 orbital, which means I'm going to mix together an s and 2 p's. But before I do that, I know in this case that I have 4 bonds, 1, 2, 3, and 4. And so I need to promote an electron so that I have 4 electrons, 4 unpaired electrons. So the first thing I'm going to do is promote. We end up with this. Okay, and then I'm going to mix, and I've run out of room, so I'm going to drop down below, and I'm going to mix. And here's the interesting thing. We already know that these are sp2 hybridized. So I'm only going to mix an s and 2 p orbitals because I know the hybridization is sp2. So what that's going to give me is 3 sp2 orbitals, right? Remember, if I mix an s and a p, that's going to give me 1, 2, 3 sp2 orbitals. But then here's the kicker. I have an unhybridized p orbital, and in this case it's got an electron in it. And so this is the deal for each of these carbon atoms. Okay, there's 3 sp2 orbitals and there's an unhybridized p orbital. And what we're going to learn in a minute is it is going to be perpendicular to the molecule. Now, I don't have models with me, and I'm drawing on a screen, so I'm going to do this the best that I can to attempt to show you what this looks like. So if I draw each of my carbons, okay, each of my carbons has 3 sp2s, and remember, we just draw them like big lobes, and they're in the shape of a trigonal planar. So I'm going to draw it like one kind of like this, one kind of like this, and one kind of going back like this. It's kind of the best I can do. Looking at my picture, they each have an electron. Now that's for my 1 carbon, but it's the same for my 2nd carbon. And then again, trigonal planar. So it kind of looks something like this. Now, if you can picture this, and I know I don't have models, but if you can picture this, this whole thing is trigonal planar. It's flat, okay? It's all in the same plane. And I forgot to put my electrons. Now, we can finish this easily with the fact that I have hydrogens attached to each of my carbons, which just come in with a 1s, and they each have an electron in them. So that's an easy, remember I'm drawing a circle because that's a 1s. There's its electron. There's its electron. Uh-oh. There's its electron. There's its electron. Okay. And hopefully what you can figure out for me is that these types of bonds are all the same type of bond that we discussed up here. Are they sigma or are they pi? Well, if you think about it, the internuclear axis is running like this, like this, like this, like this, and like this. So they're all sigma bonds, okay? And again, if I had models, you would really see that this was an end-to-end overlap. They're all sigma, and I'll label that in a second. However, what we have not done yet is this unhybridized p orbital on each carbon, and they each have an electron. And so this is where that unhybridized p orbital is perpendicular to the plane of this molecule. So I've now got I'll change my color. I've got an unhybridized p orbital, whoops, that's going to be 90 degrees or perpendicular to the bonding. And each one has an electron. So if these carbons were close enough for there to be overlap, can you see that the overlap would be occurring here and technically below also? That's not a sigma bond. That's a pi bond. So in this case, I have one pi bond and a lot of sigmas. This is a sigma, 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 and a sigma. So in C2, H4, I have one pi bond and 5 sigma bonds. And that gives me a total, of course, of 6 bonds, which is what I have. So that's interesting, okay? And that's, I know it's hard to kind of see that, and we'll do some model representation so that maybe that's a little bit easier for you. So what I want you to think about is something that we've learned. And in this case, I had a carbon-carbon double bond, okay? Well, if you look at my picture, that carbon-carbon double bond is occurring here and here. So a double bond is made up of 1 sigma and 1 pi. And that is true for any double bond, but we've proved it with this picture. So what's kind of cool later is you won't have to draw these pictures, okay, because you're gonna know that a double bond is a sigma and a pi. And maybe you can go ahead and make a guess about what all single bonds are. All single bonds are sigma. So what we've learned right now is a single bond is a sigma bond. A double bond is 1 sigma and 1 pi. And the only thing left is what is a triple bond. So let's do C2H2. Oops. Oh, gosh, go away. Okay. So C2H2. So very similar here. In this case, I have 8, 9, 10, so I have 10 electrons. My carbons are going to go in the middle, an H on the sides, and it's going to look like this. Okay, so this is a triple bond. So we can think about the hybridization at each of these carbons, right? Think about your electron domains. There are only 2, so these are going to be sp hybridized carbons. So if I think about carbon, I need to create an sp hybridized orbital. Before I do that, I know I'm going to promote an electron. And I'm going to mix enough orbitals to give me the hybridization, which is an S and a P. So what we have left, I don't think I want to call it 2. What we have left are sp hybridized orbitals, right? That came from here and here. And then I have 2 unhybridized p orbitals, which are going to be 90 degrees. So let's try to draw it. So here's my carbon, They each have sp, which comes from 2 electron domains. It's a linear relationship, so I'm going to have 180. Those are my sp orbitals, each has an electron. And here's my other sp orbitals, each has an electron. Can finish the hydrogens pretty easily. Again, they bring in a 1s. Okay, so what are we missing? Well, we've done the hydrogens, we've done this and this. What we have not taken care of is the unhybridized p orbitals that are 90 degrees to this picture. Okay, so I've got one that's just like before. Electron and electron. The other one, okay, in this case would kind of be along the z-axis, and it's hard to draw, but I'll do my best. It's the one that's going back like this and coming out toward us. And there's, I don't care where you draw the electron, whatever. There's one here and there's one here. So I've got pi bonding occurring, and I've got pi bonding occurring. So I've got a pi and a pi and a sigma and a sigma and a sigma. So hopefully we can now talk about what a triple bond is. And looking at this picture between the 2 carbons, a triple bond is 1 sigma and 2 pi's. We already learned that a double is 1 sigma and 1 pi, and all single bonds are sigma. And this is all you have to know. You'll never have to draw these pictures. Okay, but again, it's so important that you know why a double bond is a sigma and a pi instead of just memorizing that. So they could give you something like this. Okay, first of all, could we draw a Lewis structure? I hope so. So I've got 12 electrons. Carbon's going to be in the center. The other 3 are going to surround it. So hydrogen's got 4, and then 6 on the oxygen. I drew this pretty poorly. Let me move that bond just a little bit. Okay, there we go. Obviously carbon's not good, oxygen's not good, so let's maybe take these 2 and form a double bond, and that should do it. Okay, so there's my picture. So I could ask you several questions about this. And this is kind of a review of everything we've done in this chapter. So one, we could ask you about the geometry surrounding the carbon, right? So it has 3 electron domains. It should be a trigonal planar. It would be a trigonal planar electron domain geometry and a trigonal planar molecular geometry, since there are no lone pairs on the carbon. We could be asked about a bond angle here. It's got approximately 120, maybe slightly different because of this double bond, but close enough. We could also ask you to identify the hybridization around the carbon. Remember, you don't have to draw a picture. You just have to think, well, I know it's trigonal planar. That's 3 electron domains, so that carbon is sp2 hybridized. And we can also ask you how many sigma and how many pi bonds are in this molecule. So what we've learned so far is that all single bonds are sigma. So I know this is a sigma, this is a sigma. And we learned that double bonds are 1 sigma and 1 pi. So one of these is a sigma and one of them is a pi. So then you should be able to answer the question. This thing has 3 sigma bonds and 1 pi bond. And that all comes from just this Lewis structure. So that's a discussion of what sigma is, what pi is, and how it builds into this idea of hybridization. One last thing, and I'll put it up here where I wrote this kind of important box. The other thing that you should probably know is that a sigma bond is stronger than a pi bond. And that's only because the overlap is like more direct as it's along the internuclear axis. Okay, so if you just had a sigma bond and just a pi bond, the sigma bond would be stronger because it's more of a direct